All right, so time dilation continued here. We've seen in previous videos why time dilation, why time slows down. Remember the clock and so on. We'll be using that analogy here to actually develop the equations. The work that Einstein did for like general relativity, for gravity, and so on was intense mathematical processes. He had to learn new types of math like tensors and calculus and things like that to do it, to figure it out. And he enlisted help from people that were far more accomplished in math than he was. But special relativity is actually, very easy to look through and see what the consequences are. So it's literally at high school level math, and lower. Like, we're not using calculus, we're not using any of the higher end math skills. Just collecting like terms, things like that. So here we go. So just like that light clock, we've got a spaceship where we have light bouncing from one side to the other. Okay, so we're going to look at what happens from this person's point of view, observer that's in the ship, and this person's point of view that sees the ship flying by at a velocity relative to them. Right. So this person is at rest relative to the spaceship. The spaceship's moving relative to the Earth and this observer. So we've got, we know each person sees light traveling at exactly light speed, right? And so in the analysis here, see the ship is traveling a distance capital D in time little t. And so if we look at, speed equals distance over time, we can solve out for D. Say, okay, D equals the velocity of the spaceship times the time. And of course, light travels. If you see on the diagram here, light travels little d and little d again, right? It's different distance because of the distance the spaceship travels, and then plus the over. So you got a little right triangle in there, really, right? So we've got light travels 2d in time t, and of course at speed c, right? So that's the speed of light, of course, regardless of who's observing it. So we've got velocity equals distance over time. And so for light here, we've got speed c, we've got the distance 2d, we've got our t. And so if we solve for little d, we end up with ct, speed of light times time divided by 2. So what we're going to do is we're going to use those versions of things here. So we know d is this ct over 2. And so d squared is going to be, ct over 2 all squared. And then the distance here is only half of capital D, right? So we got the d over 2 squared. And then we have the length that across the spaceship here, the L, right? So L squared. So we just have, regular Pythagorean theorem. Sum of the squares, square of the hypotenuse equals the sum of the square of the other two sides, and so on, like normal. So just to work through this a bit here, we are going to multiply by 4 on that side and this side. And you can probably see why we would do that. I'll just take a, think about this as we go through. Why would that be a good idea? Well, we've got this 2 squared on the bottom, right? So it's going to get rid of that denominator. So that's really your 2 squared. And the next line here, then, without any denominators, looks kind of nice, a lot nicer already, doesn't it? Notice the little algebra steps that have happened here, right? Like the square went on to both of those, and the square went on to both of those, and so on, right? So it gave all these squares here. I'm just putting dots there to show that why that happened, if anybody's wondering. And by the way, so I can get my pointer back here. Right, so next step, algebra. Algebra case-wise here, wouldn't necessarily develop this equation from scratch without a lot of trial and error. What I want you to do right now is just follow along with the level of math we're doing here, subtracting both sides, multiplying both sides, normal math stuff. And so we're going to do a sequence of steps that are obviously correct and okay, and they're going to lead to the result that we are going to summarize. Okay, so we're subtracting the v squared, t squared from both sides. You'll see why eventually, of course. We can common factor out that t squared. Little things like that to watch for, like the idea that we could common factor out that t squared. So we have t squared times a c squared minus a v squared, right? And then we're going to divide both sides by the c squared minus v squared, which will give us a t squared equals, right? T squared equals the 4L squared over the C squared minus V squared. And then we're going to take the root of both sides for obvious reasons because it's a T squared, right? So root both sides and you end up with this. Technically, there'd be like a plus or minus kind of thing going on. So this plus sign that I added in could be anywhere really, but I mean plus or minus, and we're just going to use the plus case, basically acknowledging it, like we're moving forwards in time, right? I mentioned in the quantum section that there's an aspect of paying attention to the negative and traveling backwards in time being a thing in that transactional interpretation, if you remember. But yeah, so this time here, you notice, is from the point of view of a person seeing the ship move relative to them, right? So this is going to end up being concluded later on as I wasn't even really supposed to reveal that yet, actually, but this is going to be the one that's going to be a longer time because time's going in slow motion for people on the ship, but we'll get to that. But yeah, so we are going to, this is for later, I guess. We're going to basically, divide out that C squared. You're going to see in a second here too. So this is the common factor of the C squared, which is essentially dividing each and bringing it out front. So we have the C squared out front, which of course we root it. You can bring it outside of the root even. So we have this, the 2L over C, and then we have that root of the 1 minus V squared over C squared, right? So this time here, like we said, is relative to the Earth's reference frame, which is called the relativistic time. And I should make that a little longer of a bracket, I guess, here. Relativistic time. This is for a clock that's in motion relative to the Earth observer. Yeah, this clock. Oh, sorry, the clock. The ship itself is in motion relative to this person. So this is called a relativistic time. You're measuring something that's in motion relative to you. So the times, aren't going to be what they would normally be. Let's say. I might use the word normal carefully. You'll see in other slides here coming up. But so now we're going to analyze what is that 2L over C stuff, right? Well, 2L over C, if you look at it, is a distance over a speed, right? So it's the distance that the light is observed to go. If I go back to the L here, it's going to go there and back, right? In the original picture, 2L went there and back, right? So in that spaceship reference frame, light went there and back across the ship and back, divided by the speed of light, right? So if you look at the speed equation, distance divided by speed is really a time, right? So that's going to be the time. These are all within the spaceship reference frame. So this is the time in the spaceship reference frame. Okay, so that's the time for for light to go across and back in the ship itself at rest relative to that light clock or the photon going back and forth, right? So it's called the normal time or the proper time quite commonly. Okay, so T0 quite often used. I'll show you some other versions of that in a second here, but for now, we have the proper, actually I'll go to the next slide where the summary is here. So we've got the proper time here. And so this is just the time you'd measure for something if it's happening in front of you and it's at rest relative to you, right? So the person it's observed at rest relative to the event, sometimes called stationary time. Not super often, but I mean, from the resource, I from the government originally, it was like that. So I don't see that a whole lot in textbooks from what I have seen, but might as well see more than one type. The other T is your relativistic time, and that is turns out to be the longer one. I'll justify mathematically shortly here. And I'll come back to that one actually. Here we go. So this is the time observed for the event by an observer that the event itself, like the light going across and back, is at motion relative to, so it traces out that long path, right? And so that is the relativistic time, or just T really in most cases, but sometimes called the moving time, I guess. And then let's analyze this V squared over C squared thing. Okay, so V squared over C squared, I don't need it. So V squared over C squared is always going to be, this V here itself is always going to be less than the speed of light, as we talked about in the previous lesson, right? You can't go the speed of light or greater. Things with mass can't. And so we have that, it's less than 1, which means that 1 minus is always going to be less than 1. And so we have the root of it, which is still going to be less than 1. When you take a root, it's just going to get smaller, right? So in the end, we have this equation where we're going to know that that bottom piece is always going to be less than 1, right? And so that means when you're dividing by that, that's actually going to make things bigger. If you divide it by a half, for example, it's going to give you here, but divide by 0.1, for example, it's going to be 10 times as big, right? That's just try with your calculator. You do 7 divided by 0.1, you'll get 70 as your answer. So the example I have here is that if that number is 0.5, then we'd be dividing by 0.5, which, same as dividing by a half, invert and multiply, however you want to do the calculation, it's going to be twice as big, right? And so you have the observer would see the event taking twice as long. So this is you observing the clock as the spaceship is zipping by you, moving relative to you. You'd see it taking twice as long, right? So that's up here, where the time for the observer at rest is taking at a normal. Time for the observer at rest is taking a normal rate. The larger time value ticks. I have to be careful about how I word this here. I'm just noticing time for the observer at rest. This is. I have a whole slide dedicated to this in a second, but I'm going to have to get rid of that, actually. I was going to say at rest relative to the Earth, but really the clock is moving relative to them, right? So time for the observer that the clock is moving relative to, let's say, ship or clock or whatever. Yeah, so the time for the observer that the ship is moving relative to is ticking along at normal rate, right? And so this is gonna be a longer time because the time is slowed down for the thing that's moving relative to it. All right. So there's a computer's slow here. That's just a recap of that size business thing. So just reworded it. I just left the slide there, even though I made a new version. Just for redundancy, you get a second chance to notice it. So often the toughest part in this is the confusion between like which is the proper time and which is the relativistic time. And also even just determining what the event is, right? So we're going to look at that a little bit more here. So we have the relativistic time, which is just t, versus the proper time, which is t0, right? So we've got these two ideas here. So relativistic time is the time for an event measured by an observer that is in motion relative to the event, or the event is in motion relative to, like, doesn't matter, right? Relative motion doesn't matter. Whether you think you're moving or whether it's moving. In fact, we saw recently in a lesson that literally doesn't matter, right? It's all motions relative. George and Gracie floating in space. It could be George that was moving, or it could be Gracie that was moving, and it doesn't matter. They're both, justifiable, let's say. Anyway, so yeah, so this might be labeled as moving time, but more commonly, it's just t. And then proper time. Right? Proper time is the time for an event measured by an observer that is at rest relative to the event. Okay, and so that's pretty easy to identify as long as you can identify what the event is. We'll see that shortly here, right? So this is proper time is going to be the shorter time. It's going to be the smaller time, okay? Because it basically time slows down when things are in motion, and so it's going to be a small amount of time that ticks during the event, sometimes called stationary time. All right, so here's an example where first we're going to figure out what the heck the event is, and then we're going to look at which person's is the relativistic time, which one's the proper time. And so, excuse me, the spaceship's flying to the edge of the galaxy at a very fast speed. Okay, so what is the event? Well, the event is the ship traveling from point A to point B, right? And so think of that as an event, and so the ship traveling is the event, and then so which person's at rest relative to the event? Well, the person on the ship is at rest relative to the event itself. Like basically would be with the ship the whole time, timing how long it is, right? How long it takes. And so really what you've got is the proper time being measured by the person on the trip. So basically if you ask them, how long did the trip take? Well, the trip was going to A to B. They were in, it's kind of confusing, right? Because we've got a motion involved, the event itself. That's what I'm trying to get across, is that it can be a little bit tricky. So don't confuse the question about, being at rest relative to the event with being, quote unquote, actually at rest, which of course I hope you're recognizing actually at rest is actually meaningless, right? So what you could say is, I have a paragraph to do this actually, as an earthling, you likely still incorrectly think of intuitively the idea of being at rest relative to the earth as actually being at rest. But of course, you're not at rest right now, right? You're circling the entire earth every day as it rotates. You're circling the sun automatically every year as the orbit continues, and there's all sorts of motions, right? So this is the relativistic time here. The person on Earth watching the ship go, timing how long it takes to get to the galaxy, if you could see it, to the edge of the galaxy, if you could see it, because the event is moving relative to you, right? So weird. We'll do some more examples. Hopefully it'll start to make sense as you go. So this one, a little easier to picture. We have a particle that is moving relative to Earth. Okay, so we have a particle that's just zipping by or crashing into it or whatever, right? So again, remember, we're looking at the idea of, you can't say just because someone's on Earth that they're not at rest, whatever, right? So what's the lifetime of the particle itself, right? And so observers on Earth are at rest, and we have to finish the sentence with relative to the Earth, right? And so, it's meaningless to say at rest unless you've specified, what they're at rest relative to. So they're at rest relative to the Earth, but they're in motion relative to the particle, obviously, right? And so if we're wondering how long the particle lives, that event, the lifetime of the particle, is in motion relative to the Earth observer. Over on this side, we can point out observers moving along with the particle are not at rest relative to the Earth, of course, right? But they are at rest relative to the particle. And so, so the event, being the lifetime, is measured by an Earth observer. What that lifetime measurement would be a relativistic time. Okay, so that would be a t. Again, you might think, like, how is it a relativistic time? To think of it as the moving time and so on, right? In the other terminology. But the person on Earth is not moving. Well, they are moving relative to the particle, or the particle is moving relative to them. Both are true statements, right? So evidence of time dilation, and then I'm trying to decide whether I'm going to show the rest of this video or not, but game time decision. 1 sec.
Every second, thousands of cosmic rays, mostly hydrogen and helium nuclei, strike every square meter of the Earth's upper atmosphere. We don't really know where they come from, but we do know that when cosmic rays crash into air molecules in the atmosphere, they create a shower of other fundamental particles. Pions, kaons, positrons, electrons, neutrons, neutrinos, gamma and X-rays, and muons. We know this because we have particle detectors in labs down on the surface that detect the directions and energies of the particles in these showers, and use them to study the original cosmic rays. But there's something fascinating about the fact that we detect a lot of the muons from cosmic rays down on the surface of the Earth. Because muons, if you make them in a laboratory, only have a 1.5 microsecond half-life before they spontaneously decay into an electron or positron and some neutrinos. And yeah, the Greek symbol mu is used for both muon and for microsecond, which can certainly be a little confusing. But the lifetime of muons is really close to a microsecond, so it's also kind of beautifully appropriate. Anyway, the point is that if you have a bunch of muons, you'll only be left with about 50% after 1.5 microseconds, and 25% after 3 microseconds. And after 10 microseconds, there will only be 0.1% of the muons left. Muons don't live very long, just 2.2 microseconds on average. To put that time into perspective, light travels fast enough that in 1 second it could go around the Earth 7 times. But in 2.2 microseconds, light will only travel 660 meters, or less than half a mile. So even muons traveling at essentially the speed of light wouldn't make it more than a kilometer or two before the vast majority of them decayed, which is far less than the 10 or 20 or 30 kilometers that muons do regularly travel from the upper atmosphere to the ground. So how do muons travel dozens of kilometers through the atmosphere without spontaneously decaying, when in fact they should only be able to travel less than 1 kilometer? Time dilation. Yes, because the muons are traveling close to the speed of light, their time literally passes more slowly. At a speed of 99.5% the speed of light, 2.2 microseconds for them would be about 22 microseconds for us, enough time for the average muon to travel at least 6 kilometers before decaying, instead of half a kilometer. And even higher energy muons going even faster would even more easily reach our detectors on the Earth's surface before they decayed. At 99.995% the speed of light, the average muon would live for 220 microseconds and travel at least 66 kilometers before decaying. So from our perspective, the fact that so many cosmic ray muons reach our detectors on the Earth's surface is direct evidence for special relativity and time dilation. But what about from the muons' perspective, where they do only live?
All right, so I'm stopping there. The rest of the video talks about effects on length, because if you think of the muon's point of view, how could it possibly be reaching the Earth's surface if it knows the distance that it's traveling and how long it lives for and so on, right? So we'll get to that later. But yeah, so here we have essentially that kind of question where we have a particle that has a lifespan that's measured to be 12 nanoseconds, and that is measured by someone that sees the particle moving relative to them. So that would be your relativistic time, right? Your t, or your so-called moving relative to them time. And then so we want to determine the lifespan of the particles when measured by an observer that's at rest relative to the particles. So in other words, zipping along with the particles. So that would be the proper time. So let it catch up here. Your proper time, t0, or your so-called stationary relative to u time. Okay, so think of the m for moving relative to the observer, or stationary relative to the observer. So we have our speeds and our time and so on. They have a delta for time interval there. You don't need it, but it just means a time interval, just like the t. And so the relativistic time equation, the time dilation equation, and you can see the resource I got this from originally from the government when online courses were first coming out, I guess, or whenever. They have the S and M version, and then it's rearranged and then numbers plugged in. My preference would be just to have the time dilation equation with a t equals a t0, so relativistic time equals proper time divided by the root of 1 minus c squared over v squared. I've got the 0.6c plugged in already, and that's squared, obviously, so you're going to have a 0.6 squared and a c squared on the top, and then in the bottom you're going to have a c squared. So see the red cancellation there for that. Sec here. Yeah, the red cancellation for that c squared. If your time was given as like 2.4 times 10 to the 8, then obviously you'd just be canceling the times 10 to the 8. You can do a 2.4 divided by a 3, for example. You don't have to do 10 to the 8 divided by 10 to the 8. In this case, it's given as a fraction of c, so the entire c cancels on the top and the bottom. And so we have the root of 1 minus the c squared over v squared, which is just a 0.6 squared. And so we square it and we subtract it and we take the square root, and eventually my video will catch up here. That narrating over because my microphone turned off on me by accident. All right, so there's your relativistic time of 9.6 seconds, and notice that that's a smaller amount of time, right? That's ticked because the object's in slow motion, essentially, right? So your small number and your large number are where they should be. Paraphrasing this, just describing the end result. Obviously, the lifespan of the particles is only 9.6 seconds and nanoseconds, and it's supposed to be the 12.12 nanoseconds. According to the observer from the Earth, so it's like 25% observed to be 25% longer. So picture what that would be like for a human lifespan. You'd see people living in spaceships for 25% extra. So what do they live to? 95, 100, 110, 115, whatever it is, right? So this kind of effect, although it's real, we don't travel that fast at all in our lives, right? So you don't notice it ever in normal life. So here we go, though. If we had a space traveler that was traveling at 2.6 times 10 to the 8 meters per second for 6 months, now that's according to their time in the ship. And it has to be stated specifically what time we're talking about, right? So it's a 6-month trip according to the clock on the ship. So that's a proper time. So then if you're measuring how much time passes for people that were on Earth, then that would be a relativistic time, right? So we're going to get there here. And we'll get the time dilation equation. Obviously press pause and try it for yourself and so on. But you plug in that proper time of the 6 months, and the speeds get plugged in, and the 10 to the 8s can cancel out, as I was saying, and square them and divide and all that good stuff, right? Take the square root, divide. We're getting 12 months. So it's basically the person aged twice as much. It was 12 months instead of 6 months, let's say, right? If you're going even faster, the spaceship was going even faster, it'd be an even bigger effect, right? The time would have slowed down even more. And so it would be like 3.8 years, or for a 2.99 times 10 to the 8, it would be 6 years would have passed, right? So you'd come back as a space traveler thinking 6 months has passed, but actually, that many years has passed. This is just a page devoted to that cancellation of either the 10 to the 8 or the full C and so on. And then this is about where I realized that my microphone had stopped. So I'll stop narrating a little bit here once I catch up to the track, but I was trying to decide what to do, I think, at this point. Anyways, I have the system I use allows me to narrate. So anyways, we have a star, Alpha Centauri. It's 4.3 light years away, and so a spacecraft can travel at 0.95 C. So we want to determine how long an Earth observer would say the trip the star would take, and how long the traveler would say, right? And so it's going to kick in and go through the rest of this for you. Okay, so bear with me. In later. Yeah, I'll just add it in later. The star Alpha Centauri is 4.3 light years away. If the spacecraft could travel at a speed of 0.95 C, how long would it take an Earth observer to say the trip to that star would take? And what would the traveler say? Right? So the 4.3 light years away business is the distance from the Earth's point of view, Earth person's point of view. So we're going to look at speed equals distance over time, right? So we are 0.95 C is the speed the spaceship's traveling at. You're seeing it travel at that rate for this distance, 4.3 light years. So there's the 4.3 times 3.0 times 10 to the 8. There's the distance. And so you solve out for the time that you would see, and you get t equals, that's from the Earth's point of view, right? So that's a relativistic time, because the object is moving relative to you in that scenario, right? So there's your 4.526 business. And we put in our speeds, and we cancel out our C's, and we get 1.4 years. So only 1.4 years would pass for the people that are on the trip, because they're in slow motion, right? So their time, like they're in slow motion. And you would see them, at least anyways, in slow motion from your point of view, I should say, really. So you might notice that this result would indicate that there's a strange effect on the distance, because how can someone travel, this that far, knowing the trip distance in advance and knowing your speed? You might think it would take a longer time, right? But it only takes 1.4 years. Well, if they need to be able to travel a distance quicker, then of course the distance must have been smaller, right? So this is leading to the idea of length contraction. But there's going to be a separate lesson for that, and I'll finish the other video to deal with that when we get to it. All right, so, and there is another development at the end here for the time dilation equation, but we have gone through it enough, I believe, and so yeah, that's all for now. Thanks for watching.